This is Lecture 9H for Calculus 2 on the solution of the logistics equation. Now we're going to look at the second population model that involved the logistics equation, and here's that equation right here. Sometimes it's rewritten as this, like this, but I'm not going to use it right now. I just wanted to write that. Again, you'll see these equations many different places with different notation. I'm going to look at this equation two ways. One, I'm going to look at it graphically. The second way, I'm going to look at it analytically. All right, so let's look at it graphically first. So here's our equation right here. And when we want to look at it graphically, here's what we do. First thing we do is find the equilibrium solutions. Okay, that means we want to find the values of p such that the first derivative equals 0. Well, if you look at this equation right here, it's already factored out. Its solutions are p equals 0 and p equals the carrying capacity. Those are the equilibrium solutions. There's two of them. Now, once you find the equilibrium solutions, you look at solutions where p is greater than, let's just use m, not 0, greater than equilibrium, and you look at what happens if p is less than the equilibrium. This will tell you whether those solution curves are approaching the equilibrium or diverging away from it. So the way you look at, we've done the first step right here. That's this. We found our equilibrium, and there were two of them. Now we're going to say what happens if p is greater than m. Well, the first thing we do is look at the first derivative. The first derivative is negative. That means those solution curves would be decreasing. Now we're going to look at what happens when p is less than m. The second derivative is positive. Those solution curves are increasing. And here's what we have. If this is our equilibrium here, this is m, then if you start here, the first derivative says you're going to be decreasing. If you're out in this region, solution curves here are increasing. So we know that much about these solution curves. Now we're going to look at the second derivative and see about the curvature. Sorry about that jump on the screen. In the software, I have to turn a pen off. Otherwise, when I try to scroll, it jumps all over the place, and I hadn't turned the pen off. Okay, so what we did already was look at found the equilibrium solutions, found the values of p at which the first derivative was 0. Then we looked at solutions greater than the equilibrium and less than the equilibrium in terms of the first derivative. Now we're taking the second derivative to see about the curvature. Okay, here's the second derivative. You can go and work it out for yourself, but that's what you'll get. It's not hard. Okay, and it turns out there are 4 cases. If p is greater than the equilibrium, this second derivative is positive, the curve is concave up. I'm going to stop and draw that here, or sketch it poorly. How about that? Okay, here's time. Here's my population. That's a p, not a v. Here is m, and this is my equilibrium. So this says curves that are out here, points out here, this first derivative is negative. They're going to be going down in a concave upward manner. They'll be relaxing into the equilibrium. See that? Okay? They're concave up curves, and also they're decreasing. Now, this region is a little more troublesome. It breaks into 2 sections. Okay, let me get rid of all that writing right now. I can get the pen back. Okay, so that's taken care of and done. Now, if these all pertain to p less than m, and it turns out there's 2 regions, if the population is between the carrying capacity and half the carrying capacity, then the second derivative is negative and the curve is concave down. If the population is equal to half the carrying capacity, the second derivative is 0. This turns out to be an inflection point. And if p is between 0, population is between 0 and half the carrying capacity, then the second derivative is positive and the curve is concave up. So I will poorly sketch that again, and then we'll see some better curves of this in a minute. So here's m, Here's m over 2. Now curves in this region are increasing and concave down. They look like this. See, they're concave down but increasing. Down here, they are concave, the green one, say they're concave upward until they hit m over 2, and then they turn into a concave downward curve. So if they start down here, they have the shape which is called sigmoid. Almost looks like an S. Right at m over 2 is the inflection point, and here you're concave up, hit the inflection point, and concave down. And here is a nice graph of what I was poorly sketching before. This is your logistics equation. The equilibrium solution is going to be 200 for this example. So here's the 200 right here. The dashed line is the equilibrium solution. If the population is equal to 200, which in this case is the carrying capacity of the environment, it does not change. It just stays at 200, according to the model. Right. If the population starts at 300, it is greater than equilibrium, and that population will be decreasing, but its curve will be concave upward. See how that's concave upward? Because the second derivative is positive, although the first derivative is negative. I'm going to write that here. So here, the first derivative is negative. That's why it's going down. But the second derivative is positive, which is why it's concave up. Same thing here. When you're at like 250, you're going to do the same thing. First derivative is less than 0, you're decreasing. Second derivative is positive, you're decreasing in a concave upward manner. Okay. Now we look here between, this is m, and this is m over 2. Remember, that was an important point here. If you are greater than, if the population, the value of the population lies between the carrying capacity and half the carrying capacity, so it lies like right in here, then for this region right in here, I'm going to draw an arrow, the second derivative was positive, so the curves, the values are increasing, but the second derivative was negative, so they're increasing in a concave downward manner. See that? Okay. What happens if you're between 0 and half the carrying capacity? I'm going to draw a line through here. This is an inflection point. In this region, the second derivative is positive, so the curve is increasing, but the second derivative, did I say first? The first derivative is positive, curve is increasing. Second derivative is also positive, so it's increasing in a concave upward manner, hits the inflection point, and now you're in this other region here between M2 and M, and so it becomes concave downward. This is your sigmoid shape. Okay, now I'm going to run through the analytic solution of the logistics equation. So here's the equation we're trying to solve. It's separable. I can write it like this. Okay, I can take the p times 1 minus p over m, which can be written as m over p times m minus p, over to the other side, to the left-hand side, and leaving only the constant k. Recall that for a separable equation can be written like this. Say I'll use y as the dependent variable, and I'm going to say dy by dx just for... Okay. Here's your derivative. You can multiply it by some function. It's only a function of y, not x. After the equal sign, on the right-hand side, you have something that is a function of x only. In this case, it's a constant, but that's okay too. Now you're going to integrate both sides, and to do that first, I'm going to break this out as partial fractions. Partial fractions aren't my favorite thing, but I think this is pretty obvious. So if I had 1 over p plus 1 over m minus p, say look for a common denominator, multiply this by m minus p, I would have m minus p over the common denominator. Here you'd have to multiply by p over p, so you'd have p times the common denominator. when you combine these, you have minus p plus p. That goes away and just go at m over p times m minus p. All right, so I broke it out as partial fractions here, and now I'm going to integrate. So if I integrate 1 over p dp, I get the natural log. Right. If I integrate 1 over m minus p dp, you can either do substitution or recognition at this point. It would be minus log of m minus p. Okay. On the other side, integration just gives you kt, and then I lump everything together with this constant c. That is the end of the calculus. Totally, now it's just algebra. All right, so we had, whoa, I don't have the pen. We had the natural log of p minus the natural log of m minus p, which we can just combine. Oops, no, that wasn't the split. Okay, I can write this as the natural log of p over m minus p. I can also write that as minus 1 times that. It's no problem. So, all right. Now with a little bit of algebra, I end up here. Use exponentiation. That means you raise both sides. Okay. E to the log of m minus p over p on this side equals e to the minus kt plus c on this side. Of course, here the exponent is the inverse of the natural log. You just get m minus p over p. Here the exponent remains e to the minus kt plus c, which you can write as e to the minus kt e to the c, and I'm going to replace all this by one constant, which I'm going to call a. With a little bit of rearranging, I find the solution. P of t equals m, the carrying capacity in this case, divided by 1 plus some constant a, e to the minus kt. That constant can be evaluated. This is what it is. I'm not going to go through the steps. It's just algebra anyway. And here are the solution curves for that equation. You saw them before when we were talking about the graphical solution. Of course, it's exactly the same. It's even the same graph. So, of course, it would look the same. So, here's what I did. I gave you a catalog of the population models, starting with the simplest and showing how they increased in complexity by adding more realism, but also losing the ability to get an analytic solution. Then we went back and solved the real simple one just by pattern recognition. It's an exponential, okay, and we looked at that a little bit. Then we went to the logistics equation, which is important in many fields of study, and we solved it analytically, and we also looked at it graphically. So we saw it had that an equilibrium, actually two equilibrium solutions, one at m, the carrying capacity, and one at 0. And then if k is greater than 0, that means the birth rate exceeds the death rate. Actually, if k is less than 0, you know exactly what's going to happen. The whole thing's going to decay to 0. I mean, that's obvious. But here we want to study k greater than 0. And we found out that the carrying capacity was a stable equilibrium because all those solution curves, nearby solution curves, converge to it. But they don't converge to it in a real simple way. If it's greater than the carrying capacity, it just sort of relaxes down with a positive curvature. That's fine. If it's less than, if you start off less than the equilibrium value, m, okay, then you increase. When you're greater than m over 2, you increase with a negative curvature, so it's more like a creep function moving up into that equilibrium. But if you start far away, between 0 and m over 2, first you have a positive curvature, then a negative curvature, and this is called the sigmoid shape.